1. And as Nima was saying, this should not be a surprise because this is exactly what the unitarity perspective will tell you. Okay, that's the number of cuts you can have. That's it. Okay. Now, what I will try to show now is that the second you cannot be satisfied just with maximal cuts and just with basically nicely behaved theories in the UV, you start getting this picture in a more and more complicated way, and that's the problem that happens at higher loops. So basically, what happens is that this becomes you can do it, but it gets out of control pretty quickly. Okay, so now I will use this formalism to do something that I'm pretty sure many of you know extremely well. So how to get the Box coefficient? Okay, the 4-point function. That's, as you know, it's trivial. You just 4 cut vertices, and that's it. But whenever you have to keep track of this, situation is much more tricky. And I'm doing this because at 2 loops, we do not have the same powerful tricks that we have at 1 loop. Okay? So now let's imagine that we have a box, and we want to compute its coefficient. Okay? Now, for simplicity, let's go to a renormalizable theory. Okay? So the maximum rank that you can have is 4. Okay? So if I have a box, I can parameterize my momentum this following way. I will have the same vectors of before. I have 3 of them because I have 3 independent external legs that span my space. Okay. Then I have to invent an extra vector that still lives inside the physical space. So I will do. Oh, thanks. Sorry. So I define something that lives still in the 4-dimensional space, okay, but it's in a space which is orthogonal to the space which is spanned by the loop momenta. And then, as usual, like before, the dimensional component, which is what will create problems. Okay. So what is the general numerator of a rank 4 boxes? Well, I will have 4 loop momenta contracted with 4 external objects, polarization, vectors, whatever you want. The important part, again, they're 4-dimensional, so this will decouple. But all of this will couple. So I can separate this part here, which is written in terms of object that depends on my denominators, and this, which actually is in a transfer space. Okay, so let me write this as ni dot n. Okay, so where ni are the external states, and then sorry, not ni, sorry, ui dot l. Okay, and then u4 dot l. And I separate them because these two actually have a quite different behavior, as I'll now show. Now, remember this was L.qi. So this is basically denominators or constants, lower ranks. Okay? So every time I pick up this term here, I don't care. Job done. Okay? I go down. Okay? So I can here substitute this loop momentum. Okay? So this term here decouples. Okay? This term here gives rise to lower rank objects. Okay? But there is an annoying part now that we didn't have before. So before this was enough to go down. Now we have this term here. Okay? So this term here gives rise to n4.u4 and then l.n4. So playing the same trick we played before, we start with rank 4 and we end up with rank 4. Okay? So we didn't, it seems we didn't gain anything. Okay? It seems we were stuck. Okay? So that is actually non-reducible. Okay? But actually, we did something which is quite crucial, which is we exchanged an external random object for vector basis in the transfer space. Now, why is this useful? Well, because now I do it twice. Okay. Now I do the same thing here. Okay. And then you get, you can see, right, that this will give me something which is reducible, and then something which is not reducible, which has the same form of this. So at the end, the non-reducible part can be written like that. Okay. So here, I only have two of this. And then something which is reducible, and the only part which is not reducible is some L dot N4 squared. Okay? So basically, I'm swapping. I'm using systematically this thing here to reduce, and get back to something like that. Now, again, you may say this completely circular logic because we always end up with rank 4 objects. But now let's look at this object here. So the crucial part is that this object here lives in the transfer space. Okay? So because of this, now I can use that L squared, okay, which is my first denominator plus the mass if you want, okay, is what? Well, when I square, I will get part with denominators, propagators, and constants. This can be reduced, okay, so I don't care. Here I'm working up to denominators because every time I say denominator, the integral simplifies, okay? So something I don't care, so the constant, blah, 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 okay? And then what do I get? Then I get the square. So this with this, by assumption, is 0, because this lives in transfer space. This with this, by assumption, is 0. So what I get is just L dot N4 squared plus L dot N epsilon squared. Okay? So this tells you that if I end up with a quadratic term in the transfer space, I can use the fact that we're discussing in the break with some of you, right, that nobody cares that this is epsilon dimension, whatever. The important part is separating the space spanned by the physical momenta and something which is transverse. Okay? So here, I write that this object here can be written in terms of something which is reducible, so denominator or constant, so I go down by rank, and the price I have to pay, I have to swap for this object here. Now, this object here is the one that doesn't exist in n equal 4. Okay? So this is where problems start happening. But basically, you can play this trick over and over and over again, okay? And you can convince yourself that the most general form of a generic numerator up to rank 4 is a constant, like called d0. If you start with something of rank 1, which is linear, if it's linear in the physical space, then it's just, you reduce it. So the only non-reducible part is of this form. Okay, so if you start with something like that, there's nothing you can do. Okay. And then, in principle, you have quadratic and whatever, but everything which is quadratic, you can swap for that thing. Okay. So you can amplitude L donut epsilon squared. Okay. You can have something which is rank 3. Okay. And you can always swap it. Okay. And then at the end, so that's the most general thing that you cannot remove by playing that trick over and over and over again. Okay? And it's super annoying because I'm pretty sure, as I said, that many of you know that there's one box coefficient. Okay? And here we have 4. Okay? Now, are they real? Well, not really, right? Because now look at these objects. Okay? So this, fine, this is a constant, whatever it is. Look at this. Okay? After I integrate, so this is a rank 1 object, so this must live in the space which is spanned by the physical momenta, by the momenta that enters my loop, P1, P2, P3. Okay? And this, by assumption, orthogonal to it. Okay? So after integration, this disappears. Okay? And these objects here are all order epsilon. Okay? They all live in the extra dimension. So these are only dangerous. So this disappears, and these are only dangerous if I have singularities. Okay? Now, at the integral level, I have to check the singularities. This I don't care, and I get this, and I'm done. Okay? And in n equal 4, what turns out is that this don't exist, okay? Because the theory has a very nice UV behavior, and all I care is the bulk coefficient. So I just care about this object, so I just throw this away, and that's it. Okay? Unfortunately, in QCD, if I want to work at the integrand level, the situation is not so simple. So these are not zero, and I do not only have maximal cuts. I have lower cuts. Okay? And if I want to work with lower cuts, we will see that at the integrand level, you cannot throw away stuff that vanish after integration because they pollute your lower cuts. Okay? So you see that the situation is very clear. So there should be only one coefficient, and if the theory is well behaved, there is only one coefficient. But if I want to construct it systematically in a theory which has not such a good behavior in the ultraviolet, we will see later on, and not only maximal cuts, I have to keep a huge amount of basically nonsensical coefficients. Okay? And then you can see immediately what happens when I go to higher loops. In principle, I can play similar games. Okay? I do it loop by loop, but I start having an explosion of terms. Okay? And the situation becomes nice only if I have a nice way of directly extracting the physical information. Okay. Now, you can play as an exercise at the triangle level, at the bubble level. You just do the same thing, and the problem is that in that case, the transfer space becomes larger and larger and larger. So the number of coefficients you cannot reduce becomes larger and larger and larger. Okay. So for the triangle, for example, you have 9 coefficients. Yes.
I think for the box integral, there are higher divergences to go as like 1 over epsilon squared.
Yeah.
Do those affect the argument here?
In principle, yes. Sorry. The question is, I keep saying that QCD is bad because of the ultraviolet, but the box integral has infrared divergences. Okay. And the question is, does it affect this object here? Okay. I will discuss this later on. The answer is, in principle, yes. In practice, no, because one loop is special. This only happens at one loop, unfortunately. So what happens is that you can actually show, just by bookkeeping, just by looking at all possible singularities, is that individually, they all have infrared divergences. Okay? But when you sum everything up, they disappear. So what happens is that these objects here only give you a problem in the ultraviolet. And this, if you know n equal 4, should not be a surprise, because the infrared structure of QCD at this order, at least, is not very different. Okay, so these things are not there. Okay, so these are a leftover of pathological UV behavior. Okay, but in principle, absolutely.
Thank you.
Very good. So 4 coefficients, and as I said, if you have rank 3 triangles, you have 9 coefficients, and so on and so forth. Okay. Now, it's super annoying, and the question is, can we extract them in a reasonable way? And let's try to see. Okay. Now you know that to extract the Boss coefficient, what you can do, you can just project onto a maximal cut. Okay. So what does it mean here? Well, already this part is problematic because the maximal cut works in 4 dimensions, but here we have d-dimensional objects. Okay. Now, trust me for a second when I say that this can only give problems at one loop. At two loops is not true. In the ultraviolet. Okay, so there are no mixture in the infrared. So then, since this is ultraviolet, this is at most a single pole. Okay, so this object here, if you expand around x equal to 0, will give you just a rational function. Okay, a finite rational function. So all these are order epsilon, that they hit a 1 over epsilon pole, they will give you a rational function. Okay, and as you know, there is no way that you can reconstruct rational functions through unitarity cuts. Okay, so this is the problem. So this is the R that I was showing you before. Okay, and for now I will ignore it. Okay, I will come back later on to it. Just imagine that I have a trick that tells me how to compute this object here. Okay, and then I focus on this. Now the situation is much simpler, but still I have two and I don't like it. Okay, I should only have one. Now, in this formalism, how do I do it? And then we will see that how this makes connection to unitarity cuts. Okay. Well, I have that L is then alpha I vi plus basically L dot n4 n4, and I forget the epsilon dimensional part because I assume that I mean for dimension this I will take care separated, and I think it's completely separate. Sorry, yeah.
So before you wrote the R, and you also wrote a piece that went linear in epsilon.
Mm-hmm.
Doesn't not this R now includes pieces that are also linear in epsilon?
In principle, yes. So this is number plus order epsilon. Okay.
Okay, I see.
So what I'm saying is that I'm close to 4 dimension. I don't care. So at the end of my result, I want to put epsilon equal to 0. So I throw them away. The big problem at 2 loop is that I cannot do this. Because at 2 loop, I have, as I said, 1 loop squared like structures where these actually enter the finite result because they hit an extra pole.
I see.
Okay. But here they don't. So I do this. And this is a massive simplification. If I would not be able to do this, so if I want a good, honest, d-dimensional amplitude, then most of what I said doesn't go through. Okay, and that's a huge problem because this is exactly what happens at 2 loops.
Okay, thank you.
But in principle, yes. So this is a whole. Okay. Very good. Now we have this object here, right? And we know that L. Let's do a simple box calculation. Okay. So something like that. Okay. I have that L dot Q1 is equal to 0. L dot Q2 equal to 0. Okay. L dot Q3. Sorry, I said something stupid. Of course, it's sorry. So what we know is that L squared equal to 0. Then L plus Q1 squared is equal to 0. Plus 2 squared equal to 0. Plus 3 squared equal to 0. So this tells me that L squared, which is 0, plus 2 L dot Q1 is equal minus Q1 squared. Okay. So the cut conditions is that L dot Qi is minus Qi squared. Okay. But if you remember our parameterization, so this is exactly the coefficient alpha. So this is the nice thing of this basis. So here I can just put minus 1/2 Qi squared. Okay. So this fixes all these 3 cut conditions, and I have one last one. Okay, which will tell me something about this. Okay. So what is the last one? Well, the last one is that L squared is equal to 0. Okay. So this tells me that minus 1/2 Qi squared vi mu squared. So an object which I call n, I don't care, so a number, okay, must be equal, sign, must be equal L dot n4. squared. Okay, so that's the last condition. Okay, let me call L dot L4 L transverse, so is the transverse part, and you see immediately that this has two solutions. It's quadratic equation for L transverse. Okay, so okay, and then I see that after I substitute this, so my loop momentum, my cut loop momenta has a part which doesn't have any plus minus. So that's the part that we had before. And then plus minus N4, and then L perp plus minus. Okay? So that's the general solution of a cut condition. Okay, I have two solutions. And remember, sorry, that's one of them I wanted. Remember here the general, the most general form that my amplitude can have. Okay? So this is the unphysical one, that's the physical one. How can I extract them? Well, you see immediately that the two solutions are the same in the space which is spanned by the physical momenta, but they are opposite sign in the transfer space. Okay? So if I evaluate this in L plus in L minus, I get twice this. Okay? So this tells me that D0 is 1/2, and we call it M plus M minus, and D1 is M plus minus M minus divided some number that comes from all these factors here. Okay? So here you see, in a very obscure and convoluted way, something that you know very well, which is when you do unitarity cuts, you have to sum over all possible internal degrees of freedom. Okay? So what does it mean, this object here? Well, this object here tells you that you have propagating degrees of freedom, and you may have a left current or a right current, and you have to take the average of the two. Now, here is everything is in front of your eyes, so there is no ambiguity. It's just literally algebra. But clearly, it's not as nice and just taking a cut and taking the average. Unfortunately, at 2-loop, as I said, we don't have such a good understanding of the a good understanding of the structure of unitarity cuts to immediately get down to it. Okay. Now, as you can imagine, the situation becomes only more and more and more complicated if you go down. So this was only the box. Okay. I will not go all the way through, but I want to at least sketch the problem with the triangle to show you what happens, the kind of pain that you have to suffer if you cannot stop at the maximal cut. Okay? So what is the problem with the triangle? Just imagine I start with a box, right? Let's make a nice box, okay? And I want a triangle coefficient at the integrand level. Now, if this is non-zero and the box is non-zero, this will be contaminated by a coefficient of the box. So if I do a triple cut here, okay, I will have that this gives me what I want. So basically, the most generical numerator of the triangle evaluated on the cut. But I will have a pollution from the box. So D0 plus D1 L cut over whatever denominator is left. It's not cut. Everything on the cut. Okay. So it's non-straightforward to extract what we want, which is this object here. And as I said before, similarly to the box, that object here has a decomposition which a lot of pieces I don't care, and one piece, which is the triangle coefficient. Okay. Now, how do we do it? Well, we need a way to systematically remove the box coefficient, okay, and to extract after the triangle only the physical component like we did in the box, okay? Now, if you don't care too much and just say, fine, let's do it, in principle, you can compute d0 and d1 from there, okay? Subtract it, and you're done, okay? Now, this is what computers do. A lot of this stuff is actually implemented in numerical code, right? And since it's a computer, you don't care if you compute something which is unphysical, since it requires the same information of the physical one, so you don't waste any time, okay? So if you know d0 and d1, just subtract it, that's it, you get the cut, and then you play with it, okay? But if you want to understand how this works for real, this is not super nice. You would like to be able to access directly the physical information without having to compute non-physical stuff. You know that when you do unitarity, you try to avoid the non-physical part as much as possible, okay? Now, let's try to play the same game that we played here, okay? So we parameterize the loop momentum. And now the problem is that the transfer space, which is the one that creates troubles, becomes bigger and bigger and bigger, okay? Here we have a physical space, which is two-dimensional, okay? And I span it with whatever vector I want, I don't care, okay? And then I have a transfer space, which is spanned by two orthogonal directions. So I call it N3 and N4, okay? And for a reason will become clear in a second, I do some rotation. Okay. So basically, if you think about it, in some sense, unitarity cuts is just spherical harmonic decomposition of loop momentum. So we get something like that, okay? And as before, this object here is completely blocked by the cut condition, like before this object here. So the physical space was completely blocked by the cut condition, okay? And what is not blocked by the cut conditions are these two objects here, but there's a relation, so L square equal to 0, that relates this, the square of this to that, okay? Now, to see the relation in a nice way, I go to complex coordinates, okay? I define t plus, which is e to the I phi, okay? And I go on a complex light cone, so I define n plus minus as n3 plus minus I n4 over 2, okay? So then,
Fabrizio,
yeah.
Which case are you considering for this particular L decomposition again?
So I'm trying to look at the coefficient of a triangle.
The triangle. Okay, okay.
So of that triangle up there.
Thank you.
Okay. So basically, I have two physical directions. So let's say one and the massless one, for example. Okay, but whatever. And this defines a two-dimensional physical subspace. Okay. And then I have that my four-dimensional space is spanned by two other vectors, which I don't know. I just define two orthogonal combinations, which have the property, which are normalized, orthogonal to everything, and live in the triangle space. Okay.
And are you making any distinction between the two angles, phi plus and phi?
Where is phi plus? Sorry. It's not phi plus. It's phi. So it's the sum of two vectors.
Okay, I see. Sorry.
Sorry. Okay. So I just do this because I want to write a nice complex notation.
Okay. Thank you.
Sorry, my handwriting is horrible, so I know this. So then this becomes that L plus, defined as this P plus, okay, is V mu plus L perp, and then complex notation, I have T plus in the direction of M minus plus the other way around. Okay. And now I have this object here, okay? What is the last condition? Well, it's basically that L squared is equal to 0. Okay, this will give me a condition between this and this like before. Okay. And now I'm going a little bit quick because I don't want, I just want to sketch you, then you can do it as an exercise, okay? But just to see where the problem comes. When I plug everything in, I get that C of L plus gets something which is nice, C of L plus like before, okay? And then a complicated function of L plus here, okay? Now, in this case, contrary to the 4-cut case, I have 3-cut conditions, so I'm left with 1 degree of freedom, okay? And here I fixed everything, so my degree of freedom is T plus, okay? So what I have to care is T plus. Now, hidden here, there is a dependence of T plus, which is annoying, and I want to remove it. Now, what is the trick? Well, the trick is that this, if it comes from a box, it has an extra pole, okay? So whenever you have something with an extra pole, you can play with it and try to isolate it by doing a nice partial fractioning of your expression, okay? And what happens at the end is that if you partial fraction this object here, again, I don't pretend for you to follow all the details, but that's just linear algebra, so I'm just giving you, yes?
Sorry, maybe to go back to the idea that you have a 2-dimensional physical space, I just wanted to understand why we have 2-dimensional physical spaces. We have 4 external momenta and 1 momentum
Because you
conservation.
see, you have to look at the integral that we have, right? So we have that triangle up there. So what is this? So what is this? Let's call it L plus 1, L minus 2, okay? Something like that, okay? So this is L squared. Let's say everything is massless, but put mass doesn't change, right? L plus 1 squared, L minus 2 squared, okay? So this is a function of 1 and 2, nothing else, okay? So don't get confused by the fact that I have 3 propagators, a lot of momenta. So at the end, you have momentum conservation. So what this function knows is what is here and what is here, okay? Now, if you partial fraction it, you already know what the structure of this object here. So you must have poles, okay? Because you know that these have an extra pole. So this must have some kind of poles. And as before, it must have 2 poles because there are 2 solutions to the cut condition. So the most general solution, the most general form of the object here, and again, so this is really partial fraction. You can do it as type in Mathematica apart, and you will get this, okay? B over T plus minus T bar. There are 2 solutions, okay? And then you have a part which does not depend on T, which is a problem. Now, it turns out that the part does not depend on T, depends only on this, okay? So, and it's of the form, again, so this is just algebra, and I, where I is the index of the denominator, which is not there, okay? Dot and minus divided. The form is not important, okay? I just want to, so the details are not important. The important part is that there is a part which has poles, okay? So it's easy to identify and remove, but there is a part which doesn't have poles, okay? So it's more in these variables. So it's more complicated to remove, okay? So this is the part that comes from the box. Then there is this part here that comes from a triangle, and exactly like before, I had a part that I like and a part I don't like. Here also I have a gazillion of terms. And what turns out at the end is that if you put everything together, again, this is just algebra, I don't want to waste time on that, but you get that if I evaluate this on the cut, L plus, okay, I get the coefficient that I like, equal to C0, okay? Then I have a lot of spurious coefficients like before, like this, okay? But they're actually quite nice, so this is why one chooses that parameterization. That's a nice parameterization on the light cone of the transfer space. This makes this form manifest. So it turns out that these are horrible coefficient, but they are all proportional to this t variable, okay? Where k goes to -3 and 3, but k crucially cannot be 0. That's again, basically it's a back engineering story. So you construct variables such a way this happens. And then you have what I wrote there. So some extra pole that come from the box. And so far so good, this is trivial. And then a super annoying part, a part which is basically indistinguishable from the coefficient we like and which is contaminated by the box coefficient. So it's n I dot n minus divided to qi dot. Okay? Now, it's extremely simple to remove this without computing anything. So what do you do? Well, you define an operator that take t to infinity, does a Laurent expansion, and take the 0 term of the Laurent expansion. Okay? So if I do this, send t to infinity, this goes to 0, this goes to 0. Unfortunately, it doesn't go to 0 because I have also positive powers. But if I define it as a Laurent expansion, everything disappears apart from the k to the 0. Okay, but k to the 0 is not there. Okay, so this disappears. So this, for the one of you who know one loop unitarity, this is the inf operation that people define in the triangle coefficient. If you don't know what it is, it's that thing. Okay. Only here it's done in a formal way without any specifying any normalization. But we have a problem. We have a contamination of the box that doesn't go away. Okay. So we found a parameterization of momenta that makes things nice, but not as nice as we would like. Yes.
I don't understand this inf operation. Well,
Okay, so
t comes from partial fractions, so it should have some dependence on the external momenta or some.
no, you see, t is just a parameterization of the object here. Okay, so I parameterize my loop momenta like that. Okay, so here I have all external momenta, whatever. Okay, and this is just, if you want, a parameterization of this extra angle, which is not fixed by anything. Okay? So what is happening is that, sorry, I'm being quite fast, but again, I just want to show the problem. So what happens is that I have four loop momenta. I have three conditions, so I fix three. Okay? So there will be one variable which is integrated over. Okay? And what I'm trying to do here is to define a parameterization in such a way that this variable is such that I can use it to immediately spot everything I don't like. Yes. Okay? And this variable is t. So if you want, t is the remaining integration variable. Okay? And why I write it this way? Well, I write it this way because I back engineer this result. Okay? So if I write it this way, I know that I must have poles in t coming from the box, and that I make them disappear when t goes to infinity. Okay? I have a spurious triangle coefficient that I didn't write down, but you can try to do it as an exercise. Okay? And it turns out that they all like that. So they are either t to some positive or negative k, but never t to the 0. Okay? So if I define this inf object, like do the Laurent expansion at t equal to infinity and take the 0th order coefficient, so that's a formal definition, so then this disappears. Okay? And the one that does not disappear is this. And again, so I found the parameterization which is quite good. It basically kills everything apart from one thing. Okay? But it's not enough. I want to kill everything. Okay? And now the trick is we said there are two solutions to this cut condition. And it's easy to see that the second solution is the one with minus here. Okay? You do the same identical game with minus. Okay? And you sum the two. Now this is just a number. Okay? Becomes itself divided by 2, 2 itself divided by 2. And this becomes this plus the same thing with plus, okay? And as you can imagine, just do it as an exercise, so this thing cancels, okay? So you see that what we expect to happen, so that this, in 4 dimensions, for each, there is only one non-trivial coefficient, and we have these structures, actually happens. But if we don't have direct access to unitarity cuts, it's a complete mess, okay? It's a complete mess, it is hidden, and there are all these non-4-dimensional objects that conspire against us, okay? So that's a big difference that we have in QCD respect to n equal 4. And at one loop, it's fine, because we can easily do this, okay? So this is, you can do it on a piece of paper, okay? But this becomes more and more cumbersome if you start going higher and higher and higher. Okay, sorry, I don't remember when I'm supposed to stop. Okay, so I have 15 minutes. So the plan was to basically show the direct connection between this and the unitarity approach. So basically compute the one loop box with unitarity cut and see that it's exactly the same. I'm pretty sure that many of you already saw this. Okay, so you just take one loop box and you cut it. So I will skip it. If you don't have seen it and you would like to see it, we can do it at some point. Okay, so the point is that this gives you a very, very dull, if you want, way of systematically creating everything. And if we have access to the unitarity part, this becomes very, very simple. But if we don't, this becomes quite complicated. And as you can imagine, the more you go down, so the box was okayish, triangle is bad, the bubble is disgusting. Okay, so the more you go down, and the more you go down, it means the worse your theory is in the UV. Okay, so you're basically removing denominators. You get explosion of terms. And at one loop, there are tricks to extend them in a nice way. But what I'm trying to convey is that already at one loop, the situation becomes complicated. And not conceptually, but just you have an explosion of terms. And this doesn't help you, and doesn't help you so much. Okay? But what is the power at one loop, at least? Well, at one loop, we have one way. So we have a fixed number of master integrals, okay, box, triangle, bubbles. And we have one way, which is a little bit cumbersome, but can be made very, very sharp from unitarity, of projecting our amplitudes directly on the master integrals. Okay, so that's the trick. So at one loop, we can sidestep all complicated constructions and go straight to the result, at least in 4 dimensions, because we can do this projection. Okay, and the projection is unique and simple. And that is the problem at 2 loops. We have ideas of how to do these projections made by our people in the first row, but we still have to develop it in a coherent way, as I will try to argue later on. But before going there is a big problem. I didn't say anything about these rational terms. Okay? I hope that by now it's clear that all these objects are order epsilon, so this becomes problematic if and only if the integral develops singularities, develops poles. And one thing that it's quite nice at one loop, I will not prove it because it's basically not particularly illuminating, is that this object here, as I said before, vanish in the infrared. Okay? So how do you prove it? Well, you have the most generic loop parameterization. You write the most generic loop integrand, and you can check, similar to what we did before for the 5-point, that in any possible limit, this conspires to kill the infrared singularity. Okay? You can do it as an exercise. It's not difficult. It's a bit boring, so I will not do it. Okay? And crucially, this doesn't happen at 2 loops. At 2 loops, you have these terms both in the ultraviolet and in the infrared. It's not clear whether this is for real or not. Okay? So it may be that we don't understand how to arrange the 2 loop amplitude in a nice enough way to remove non-physical information. And it may very well be, and it would be very nice if it happens. I mean, morally, you would really like something like that. That something similar, if you do things properly, then there is some cancellation of these terms as well. But as of today, at 2 loops, we don't have this cancellation, and we don't have a general way of extracting them. Okay, so at 2 loops, this is a problem. Okay, now in the infrared. What about, there are some results in QED, but not in QCD. What about the ultraviolet? The ultraviolet is there, okay? And basically these are there because, as I said, the QCD compared to n equal 4 has a not so nice UV behavior, okay? Which is annoying, but on the other hand, UV is simple, okay? Because UV, when you go to the UV, you can neglect all external states and whatever. And if you think about normalization, typically in the UV, what happens is that you shrink subdiagrams to a point, add the counter term, and that's it, okay? So you would imagine that somehow getting the UV part of the story is not super complicated, okay? And actually, this is exactly what happens. So you know, again, I don't want to go into the details. If you're interested, you can ask me, and we can do an example. But I don't have time to go through it, because at some point we want to move to other stuff. But what happens in the UV is that this basically hits, so these are order epsilon object that hits 1 over epsilon of transcendental function. The 1 over epsilon transcendental function doesn't have any log, any nothing, okay? So it's a constant, or sorry, it's a rational function. So this will be, as I said, rational, okay? And you can think of what you do with normalization. So just imagine you have something like that, which has a UV singularity, okay? And what you do, you write it as itself plus a counter term. Okay, so this is how you do renormalization, okay? And you can imagine if you are a little bit careful, and when you do this normalization, you don't consider only poles, but also possible leftover, a very, very similar situation must happen. And again, I don't want to go into the details, but it is possible to prove that basically the same structure that happens in normalization happens for the calculation of these rational terms, which is super nice because this removes one loop. Okay, these are local counter terms. So basically, this defines a set of Feynman rules, or modified set of Feynman rules, like renormalization. Okay, set of counter terms if you prefer, if you don't like Feynman rules, that are theory dependent and allow you to completely extract the rational terms. And you can try to do it in QED. This is quite simple. Now, they're related to normalization, so this only comes from UV divergent stuff. So as for normalization, let's say in QED, you just need 4 sets. Sorry, 3 sets. Okay. So you define 3 basic Feynman rules, and you can construct the most general amplitude starting from this object. Okay. Now this has been known since before I started my PhD, so a long time ago. Okay. What is more new is what happens at 2 loops. Okay. Because at 1 loop everything is simple, so the fact that it's a rational function is fine. It's an interesting question whether similar structure persists at higher loops. Okay. And the answer is yes. So basically, the same stuff that you do when you do standard Bogoliubov of renormalization, it happens here as well. So if you want to do this at 2 loops, you get the usual thing that you define a renormalization amplitude associated to a graph, okay, which is your original amplitude, and then you have a counter term, okay, some overall 1 loop counter term for the subdivergent graph, okay, so the usual stuff. So you have your original graph where you shrink to a point the subdivergence plus a genuine 2-loop renormalization. This is standard normalization, okay? Thanks. Standard normalization. And what happens is that all you have to do to get these UV rational terms is slightly modify the counter term, and you capture everything. So this again tells you that you can define counter term-like structure that allows you, even at 2 loop, to do basically everything in 4 dimension and then capture the dimensional part as long as the UV goes. The infrared is more complicated, okay? And if you want more information about this, so 2001.11380 is where they did it at 2 loop. And last year, Claude Dura and friends proved it at all loop order. So at any number of loops, you can define renormalization-like procedure to extract these rational terms. Maybe difficult, maybe easy, it's irrelevant, but conceptually it's understood. Okay? And again, so these are objects that comes because of the bad UV behavior. And you may say, okay, this is super annoying. Do we actually need them? And the answer is yes, we absolutely need them. And to show you why we need them, and this will be probably the last thing I will do today, I will show you a structure of a QCD one-loop amplitude and emphasize the huge difference with respect to n equal 4. Okay. Now I take something very simple. So now let's consider a 4-gluon amplitude at one loop. Okay. And we consider only the contribution coming from closed fermion loops. Okay. So I consider this amplitude here. Contribution proportional to the number of fermions. And the reason is simple because whenever you have closed fermion loops, the word anomaly should start blinking in your head, and indeed it will happen. Now, let's imagine we have a theory which is parity invariant, like QCD. Okay, so these are vector light fermions. Okay, they're not chiral. What happens? Well, you can compute the full amplitude. It's a simple exercise. You can do it almost over lunch. Okay, and you find that the one-loop amplitude is proportional to 3 level times some nice structure. So we have coefficient, use box, bubble, triangle, everything. You don't need to write it down. I just want to show the structure. Okay. Log square minus d minus s. So with this minus c minus s, I mean the usual thing that these things must be analytically continuous by giving a positive imaginary part to the invariance, the usual thing. Okay. So this is part of the result, and then I'm not used to the last one, doesn't go up. So ours is infinite, so it's a circle. So sorry for going backwards, but then we get other part, okay, which is s minus t. And again, I don't care about the form. I just care about the singularity structure. Divided by 3u minus st over u cube s minus t. Okay. Log minus s over minus t. Okay. Plus the usual thing comes from infrared divergences, sorry, minus. You have minus s to the minus epsilon plus minus t to the minus epsilon, then your infrared pulse. Okay. And then plus rational. Okay, and that's very different from what you have in n equal 4, where this doesn't exist. Okay. But just imagine that rational is not there. Do you see any problem? Just imagine that rational is 0. We just made a calculation, a mistake, and this thing is 0. What happens? So which kind of singularities you would like Ramses to have? Unitarity plus locality? Can you have something like that? Well, when someone asks the questions, the answer is always no, right? So you see, these amplitudes without rational terms has humongous spurious poles. Okay, you can have such higher poles in something which respects unitarity and locality. Okay, so you have nice poles and branch cuts, but you cannot have this horrible nonsense. Okay, so this come from again bad UV behavior. In n equal 4, you don't have anything like that, and this object here is absolutely crucial to cancel that object, that pole. Okay? And actually, in this simple case, this case is so simple that you don't even need to compute it. You just ask that the poles are cancelled, and this is a colored amplitude, so it must be cyclic and whatever. So you can just guess what the result is. So if you expand everything, so if you expand this as small u, you get that this is minus s squared over u squared minus s over u, okay? And then this you can write it, sorry, plus the expansion of this rational. And in order for this to cancel the pole and have all the proper symmetries, you can easily convince yourself that the only form you can have which is consistent with everything is this. Okay? So in this simple case, you can fix everything, but it's not important. In general cases, you cannot. But the important part is that in QCD, because of this bad UV behavior, you have a lot of junk that makes your function not pure. Okay? And basically forcing yourself to use pure functions or logs in this case, where everything is simple, actually is not good because it leaves a spurious poles implicit. Okay. So what happens to one loop is that it's very easy because one loop is simple to define a new basis of function which are not pure, which is basically log divided by rational terms, such a way that you reabsorb all this horrible nonsense. And when you do this, the answer becomes very, very simple. Okay. So you see, this is very, very different from the paradigm that we have in n equal 4, but it's a problem, and we don't know how to do this systematically at two loops. Okay, so we don't know how to make this manifest. Now, I think I have 2 minutes, right? So the last thing I want to give you is an exercise. Now, just imagine that your theory is not vector-like fermions, but you have chiral fermions. Okay. So the second you have a gauge theory with chiral fermions, you start shaking because the theory basically has serious chances of disappearing in front of your eyes. And let's try to see what happens here. Now, there is one small subtlety here. So this cancels the nice poles, okay? The bad poles in U of that object there, so it's fine. But it's multiplied by 3 level, okay? Which has itself poles in S, T, and U. So you want this to cancel poles in U without introducing any extra spurious poles, okay? And here you see everything happens nicely because S and T in the numerator cancel all possible S and T poles of the 3 level, okay? So this conspires to do exactly the job, okay? Now what happens if now you have a chiral theory, okay? So you basically have left-handed fermions moving around, okay? Then it turns out that for chiral theory, the rational term is S minus T divided 2U A3, okay? And now you have big problems because you have that the U pole is taken care of, but this is introducing wrong pole in S and T because this alone are not enough to remove the poles here. Okay? So in a chiral theory, it seems that you cannot have a nice local unitary result. Okay? But remember, these are partial amplitudes. Okay? So this will be multiplied by color structure. Okay? Let's say these are traces. Okay, and this, let's say that this comes with a trace 1, 2, 3, 4. Okay, and then you see if I swap basically, if I go in the opposite direction, okay, so trace of 1, 4, 3, 2, I get the same thing as chiral. I can pick up a minus sign. Okay, so when I put everything together, the coefficient which is proportional to is 1, 4, 3, sorry, 1, 4, 3, 2, so the other direction, pick up a minus sign because of the chiral nature of the fermion, okay? And you get something like that, okay? Now, that thing cannot exist in a nice theory, okay? And now it's a simple exercise for you to expand this object here. You will find that you want this to be 0. Otherwise, your theory is inconsistent, okay? Doesn't respect unitarity and locality. And what you find, just expand those things here, is that this D, A, B, C, F, D, E, A, this to be 0. And for the one of you who play with anomalies, this is exactly the anomaly cancellation condition for the box anomaly. Okay, so you can derive that the theorem must be anomalous is free directly by imposing locality and unitarity. You can do it as an exercise because it's pretty nice. Now, the one of you who really likes string theory, there is a d minus 6 in front of that thing. Okay, and you may start to think, okay, what happens then in d equal to 6? I'm not going to tell you. You can try to think about it, and we can discuss if you want. Okay, so just imagine what can happen in 6 dimensions. And I think I'm already over time, so we'll continue tomorrow. Thank you very much.
All right, thank you, Fabrizio. I suggest that in the interest of time, we just postpone all the questions, and then we'll be back at 12, so in 15 minutes. Let's thank Fabrizio once again.